Hello everyone, welcome to the channel. In today's video, we'll be solving some problems on mean value theorems, which are of ISICMI style. In the previous video, we discussed the proof of each mean value theorem and also some other theorems like Taylor theorem, Darbox theorem. Today, we'll be solving problems on basis of these theorems. If anyone hasn't watched the video of the proof of these theorems, I recommend you to go to that video, which is on the same channel, and then come back to this video. You can pause and try the problems that will be coming on the screen before seeing the solution. Let's go to the first question. Let f comma g be differentiable on closed interval a comma b with f of a equal to f of b equal to 0. G of a equal to g of b is equal to 0. Prove that there exists c belongs to a comma b such that f of c by g of c is equal to f double dash of c by g double dash of c. In this question, we are going to do some sort of like reverse engineering that will use the result to see what function we can create so that we can apply Rolle's theorem on that function, and then we can say that there will exist a c such that this result will hold true. So now first let's break down this result. Let me write down the result. We'll take the RHS onto the left hand side. I'll get f of c into g double dash of c minus f double dash of c into g of c equal to 0. I wantedly ignored the denominator part because it will only contain g of c into g dash of c. From the question we can see that they both can't anyways be 0 at any intermediate value between a and b. So now we have something looking like this. Now what I'll do is I'll define a function h of x is equal to f of x into g double dash of x minus f double dash of x into g of x. Now somehow I can prove that there will exist a c such that h of c will vanish. Then I can get back to this result which will give me this result. So now my ultimate aim is to find a c that will make h of c 0. Now let's try to do that. Now I'll do a manipulation here. I'll add and subtract f dash of x into g dash of x. Now you may ask, why did I do this? If you can properly observe, this is in form of the product rule. This is also in the form of product rule. I can write h of x is equal to d by dx of f of x into g dash of x minus d by dx of f dash of x into g of x. Now I'll integrate on both sides. Let's do one thing. Let's define a new function p of x is equal to integral h of x dx. Now if I integrate on both sides, I will get that p of x is equal to f of x into g dash of x minus f dash of x into g of x plus constant of integration. Now let's see the boundary conditions. F of a is equal to f of b is equal to 0. G of a is equal to g of b is equal to 0. Now if I put x equal to a in p of x, I'll get p of a is equal to, here f of a will become 0, here g of a will become 0. I left with the constant c. And again, if I put in b in place of x, f of b will vanish, g of b will vanish. I will be left with constant. Now this implies that p of a is equal to p of b. Now from Rolle's theorem we can say that there exists c belonging to a comma b such that p dash of c is equal to 0. Now what is p dash of c? It is nothing but h of c is equal to 0, which is what we were trying to prove. Now this will again bring us back to this equation. When I put c, this LHS will vanish and I will be left with f of c into g double dash of c minus f double dash of c into g of c is equal to 0, which will give me that f of c by g of c is equal to f double dash of c by g double dash of c. This is the proof of our first problem. You can observe what we did here. We took the result itself, and from there we took an idea of what function to consider, and then we did some manipulation, and then finally applied Rolle's theorem to prove that there will exist a c such that this will have a root, and which in return gave us our result. I hope everyone understood. Now let's move on to the next problem. Define f from closed interval 0, 1 to r be differentiable such that f of 0 is equal to f of 1 is equal to 0. Integral 0 to 1 f of x dx is equal to 0. Prove that there exists c belongs from 0, 1 such that f dash of c is equal to integral 0 to c f of x dx. Now even this problem is not so different from the first problem. The idea is the same. Let's analyze the result. It says f dash of c is equal to integral 0 to c f of x dx. Now let me do one thing. I will define capital F of x is equal to integral 0 to x f of x dx, which means that f dash of x, capital F dash of x is equal to small f of x, double derivative of capital F of x is equal to small f dash of x. Now if we substitute this terminology in the given result, we will get that capital F double dash of c minus capital F of c is equal to 0. Now you can see that what function we are going to define. Let h of x is equal to f double dash of x minus f of x. Now again what I'll do is I'll add and subtract an f dash of x, f double dash of x plus f dash of x minus of f dash of x plus f of x. Now to make it look like the product rule form, I will multiply with an e power x on both sides. Power x into h of x is equal to e power x into capital F double dash of x plus f dash of x minus e power x into f dash of x plus f of x. Now you can see that this is of the form product rule and this is of the form product rule. E power x h of x is equal to d by dx of e power x f dash of x minus d by dx of e power x f of x. Now again I will define integral e power x h of x is equal to p of x. Now integrating on both sides, I will get that p of x is equal to e power x f dash of x minus e power x f of x. Now let's see what were the initial conditions given so that we can apply Rolle's theorem. It says f of 0, small f of 0 equal to small f of 1 is equal to 0. This means that f dash of 0 is equal to f dash of 1 is equal to 0. This means that f of 1 is equal to 0. And you can see that when I put x equal to 0 in this integration, 0 to 0 is 0 itself. Therefore, we can say that capital F of 0 is also 0. Now, what will be p of 0? P of 0 is when I put x equal to 0, f dash of 0 is 0. And f of 0 is also 0. I'll get 0. Okay. There is an integration constant. I'll be left with the integration constant itself. When I put 1, I'll again get 0 plus integration constant. This means that p of 0 is equal to p of 1. Now again from Rolle's theorem we can say that there exists c belonging to 0, 1 such that p dash of c is equal to 0, which is nothing but e power c into h of c equal to 0. Since e power c cannot be 0, this will mean that h of c is equal to 0. We have defined h of x as capital F double dash of x minus capital F of x. Now when I substitute c, this h of c will vanish and I'll get capital F double dash of c is equal to capital F of c. Now I will write them in the original forms. I will get the f dash of c is equal to integral 0 to c f of x dx. This was the result we were needed to prove. Hope everyone understood. The idea is same. We have just done reverse engineering, seeing the result. Now let's move on to the next problem. Our next problem is taken from this year's CMI 2026 part B. Though the question is not exactly framed, but the idea is same. Let f be differentiable on closed interval 0, 1 with f of 0 equal to 0, f of 1 is equal to 1. Prove that for every positive integer n, there exists c1 till cn belonging to 0, 1 with summation of from running from k equal to 1 to n, 1 by f dash of ck is equal to n. Now in this question, we will be using intermediate value theorem and Lagrange's mean value theorem. Before I write the proper answer, I'll just explain you the idea, what I'll be going to use. Now since f of 0 is 0 and f of 1 is 1, from intermediate value theorem, I can say that there exists a1 belonging to 0, 1 such that f of a1 is equal to 1 by n. Now if I apply LMVT on the interval 0 to a1, we can say that f of a1 minus f of 0 divided by a1 minus 0 is equal to some f dash of, let's say, c1, where c1 belongs from 0 to a1. Now f of a1 is nothing but 1 by n and f of 0 is 0. This will mean that I'll get 1 by f dash of c1 is equal to n times a1 minus 0. Now similarly, when I travel from 1 by n till 1, I have to cross 2 by n. From intermediate value theorem, there exists a2 belonging from a1 to 1 such that f of a2 is equal to 2 by n. Now if I again apply LMVT on a1 to a2, I get f of a2 minus f of a1 divided by a2 minus a1 is equal to f dash of c2. c2 will belong from a1 to a2. Now again I get 2 by n minus 1 by n as n, 1 by n, and I'll get 1 by f dash of c2 is equal to n times a2 minus a1. Now I'll construct a sequence like this and add up all the terms. You can see if I add these both, the a1 will be cancelled. Now if I write the third term, the a2 will be cancelled. So on I travel, in the end I'll be left with n times 1 minus 0, which is nothing but n. Now let me write the proper answer. And we'll say define a quantity k such that k belongs from 0, 1, 2, so on till small n. This will imply that k by n will always be greater than or equal to 0 and less than or equal to 1. When k equal to 0, the equality hold true on the left hand side. When k is equal to n, the equality will hold true on the right hand side. Now since this will hold true, then from intermediate value theorem, we can say that there exist a0, a1, a2 till an such that f of ak is equal to k by n. Now we know that f of 0 is equal to 0. This will mean that a naught will be equal to 0 in the sequence, and we know that f of 1 is equal to 1. This will mean that an will be equal to 1. Don't get confused that an is the general term. Here ak is the general term and n is just a constant value. Yes. Now we define the sequence. Now I'll apply LMVT in the interval ak minus 1 and ak. I'll get f of ak minus f of ak minus 1 divided by ak minus 1 is equal to f dash of ck, where ck will belong in between ak minus 1 and ak. Now if I substitute the values of f of ak and f of ak minus 1 and then take the reciprocal, I'll get 1 by f dash of ck is equal to n times ak minus 1. Now I'll apply summation k equal to 1 to n on both sides. I will get that sigma k equal to 1 to n. I can take this n out common since it doesn't depend on k. ak minus 1. This is a telescopic series. After I do the summation, I'll be left with an minus a naught. An is nothing but 1 and a naught is nothing but 0, as we have said in our previous slide. So this thing is nothing but n. So therefore we said that. Now again you can also see that since ck belongs from ak to ak minus 1, all this c1, c2, c3, so on till cn will be distinct constants, such that when we add all of their 1 by f dash of ck, we will be getting n. So therefore we can say that there exist c1 till cn such that summation k equal to 1 to n 1 by f dash of ck is equal to n. I hope everyone understood. Now let's move on to our next question. It says let f be a twice differentiable function on open interval a comma b with f of a equal to f of b equal to 0 and f of c is greater than 0 for some c belonging to a comma b. We need to prove that there exists k belonging to a comma b with f double dash of k is less than 0. Now you can prove it in two ways. Let's say method 1. Method 1 is using LMVT. Now we are given that there will exist a point f of c greater than 0. Now I'll break my intervals for LMVT as 0 comma c and c comma 1. If I apply LMVT in this interval, I get f of c minus a and b. F of c minus f of a by c minus a is equal to f dash of, let's call it p. P belongs from a comma c. F of c is nothing but, it's just a positive quantity. F of a is given 0. Therefore we get f dash of p is equal to f of c by c minus a. Now similarly, if I apply LMVT on this interval, I get f of c minus f of b by c minus b. It will be f of b minus f of c by is equal to, let's say, f dash of q, where q belongs from c comma b. Now what I'll be doing is, f dash of q is nothing but minus f of c by b minus c. Now since f is a twice differentiable function, I'll again apply LMVT on the interval p to q using this information. I get f dash of q minus f dash of p divided by q minus p is equal to f double dash of, call it k. K belongs from P to Q. Now if I substitute the values that I got before, I will get that minus of f of c by c minus a plus f of c by b minus c divided by q minus p. Now we know that c is a quantity that is greater than a, and f of c is also a greater than 0 quantity. So therefore this quantity is positive. Similarly, b is greater than c and f of c is greater than 0. Therefore this is also a positive quantity. And since q is greater than p, q minus p is also a positive quantity. Therefore this whole thing is a strictly positive quantity. When you multiply it with a minus, it will become a negative quantity. This will mean that f double dash of k is less than 0, where k belongs from p to q, where p and q lie in between a and b. So therefore we can say that k will lie in between a and b. Now method 2 is interesting. We can use Taylor theorem. Now since f is a twice differentiable function, can define f of x is equal to, let's take some intermediate point m belonging to a comma b, f of m plus f dash of m divided by 1 factorial into x minus m plus f double dash of some constant c1 into x minus m whole square divided by 2 factorial. We have discussed about Taylor theorem and its proof in our previous video. You can check it out. Yes, now we got this from Taylor theorem. Now since they said that f of a is equal to f of b is equal to 0 and f of c is greater than 0, from extreme value theorem we can say that there exists a positive maximum for this function. Let's make that point of maximum to be m comma f of m. The purpose of doing this is, we can say, since at the extreme point from Fermat theorem f dash of m will be 0, this will make our calculation even easier. We can write this term as 0. I will be left with f of x is equal to f of m plus f double dash of c1 by 2 factorial into x minus m whole square. Now if I put x as a, now and also c1 will belong from m comma x. Now if I put x equal to a, I will get f double dash of c1 as minus f of m into 2 divided by a minus m whole square. Now since we defined f of m to be the maximum, therefore f of m will be a positive quantity, and also a minus m whole square is also a positive quantity. Therefore this whole thing is strictly a positive quantity. When you multiply it with a negative sign, this whole thing will be strictly less than 0. Therefore f double dash of c1 is less than 0. Here you can also do another thing. Instead of putting x equal to a, you can put x equal to b. Now we will have a different constant c2. Since let's say c1 is lying between m and a, c2 will lie in between m and b. I will get f double dash of c2 is equal to minus f of m into 2 by b minus n whole square, just a change of variable. Now again this whole thing is a strictly positive quantity. Multiplying with it a minus, we get less than 0. Therefore we can say that not only one, but there exist two distinct c1, c2 such that f double dash of k is less than 0. Now let's move on to our next question. Let f from closed interval 0, 1 to r be a twice differentiable function with f of 0 equal to f of 1 equal to 0. Given absolute value of f double dash of x is less than or equal to capital M, where capital M is obviously a positive real quantity. We need to show that absolute value of f of x will always be less than or equal to m by 2 into x into 1 minus x for all x belonging to 0 to 1. Now in this question we have been given information about f double dash of x. We don't know anything about the single derivative. So applying Taylor theorem would be the best choice. Now let me write the Taylor theorem. Let me choose some arbitrary point between 0 to 1. Let p belong to 0 comma 1. Then I can say that f of x is equal to f of p plus f dash of p into x minus p plus f double dash of p into x minus p whole square. Sorry, this is not p, it is some constant c where c belongs from p to x. Now when I put x equal to 0, now similarly when I put x equal to 1, I get 0 equal to. Now what I'll do is, from these two equations I'll eliminate f dash of p so that I can then take an absolute value and then put this inequality and then get an inequality for absolute value of mod f of p. So now let's eliminate this. In order to eliminate this, I'll multiply equation 1 with 1 minus p and equation 2 with p. I'll get 0 equal to f of p into 1 minus b minus f dash of p into 1 minus p plus f double dash of c1 into p square into 1 minus p. Now I'll multiply with p on the second equation. I'll get f of p into p plus f dash of p into 1 minus p plus f double dash of c2 into 1 minus p whole square into p. Now if I add both of these equations, I can see that these terms will get cancelled and I'll get 0 equal to, when I add both of these terms, this minus p and p will get cancelled and I'll have f of p and plus the single derivative thing will be cancelled, and then in the double derivative I'll have f double dash of c1 into p square into 1 minus p plus f double dash of c2 into 1 minus p whole square into p. Now I'll take this to the LHS and then apply absolute value on both sides. Mod f of p is equal to mod of, I can take p into 1 minus p common. Since it is a positive quantity, I'll not put any absolute value. F double dash of c1 times p plus f double dash of c2 times 1 minus p. Now here on these terms I can apply triangle inequality, which is mod a plus b is less than or equal to mod a plus mod b. I'll get mod f of p is less than or equal to p times 1 minus p into mod f double dash of c1 times p plus 1 minus p into mod f double dash of c2. Now since we know that mod f double dash of x is less than or equal to 10 for all x belonging to 0 comma 1, I'll now apply this inequality here and I'll get mod f of p is less than or equal to capital M into p times 1 minus p, and then adding these both up, they will get cancelled and I'll be left with this. But with our original result had by 2, there has been a small error. I have forgot to divide this thing with a 2 factorial, and finally here also we'll have a 2 factorial, and then when we substitute this we'll have the 2 left here. Yeah, this was the result we were to prove. Now since P is any arbitrary point in between 0 to 1, so therefore we can conclude that absolute value of f of x will lie in between, it will be always strictly less than or equal to x into 1 minus x for all x belonging to 0 comma 1. Now this question could also be framed in another way to make it look fancy or scarier. We could say you to prove that maximum mod f of x belongs to 0 comma 1 is less than or equal to m by 8. Now we can also easily see that when p is say like something like 1 by 2, you'll have m by 2 into 1 by 2 into 1 by 2, which will give you m by 8, which is nothing but the maximum value of this quadratic. So therefore the maximum value of this modulus of f of x will always be less than or equal to m by 8. They could also frame the question in this manner to make it look scarier, but our idea would be the same, to use Taylor theorem and get till here. I hope everyone understood. Now you can try some problem. This is a homework problem 1. And now the other question is from Putnam 2015. It says let f be a thrice differentiable function such that f has at least 5 zeros. You can say that those 5 zeros are distinct. You need to prove that this equation, so this expression, will have at least 2 distinct zeros. The problem is based on Rolle's theorem. The problem is not identifying Rolle's theorem, but to see which function to take and then apply Rolle's theorem. I have left you with an hint that dy dx of e power ax f of x is equal to e power ax into af of x plus f dash of x. Whoever puts the solution of this question in the comments, I will pin their comment. I hope everybody understood today's class. Our next video, I'll bring some more problems of these types. I hope everybody understood. Thank you. Take care. Goodbye.